Okay, let's take a look at all these questions together. Well, I would say most of them are very easy. I just want to share with you how you can think about this, what to think, and how to be better, be good. Okay, so for the first one, now I know there's a temptation to write stuff down. Please don't. Please don't. Just put it in your head and force it to think. And you need that mental capacity, not just for math. You need that. So you stare at this question, you're like, wait, hold on, what can I see? What can you see? Okay, the secant x becomes one of a cosine, so you have the numerator as sine x, the denominator as cosine x, so that is just tangent x, and that would be the letter G. Okay, that's letter G. All right. Number two. Now for number two, so you have this. These are the odd function, even function stuff. So when you look at this, you need to know, okay, this is the even function, odd function stuff. Which one is odd function? Which one is even function? Okay, sine is the odd function, so that's why the negative goes to the front, because well, that's what odd function does. And a cosine is an even function, so that's why the cosine of negative x is the same as cosine of x, and that gives you negative of tangent. That would be the letter N. All right, for number three, so there are a couple of things right here. They're all like, when you see the square, then, well, the most immediate connection that you can make is Pythagorean identities. 1 minus sine square x is cosine square x. So you kind of hold it in your head, like, okay, so I can see the numerator being cosine square x. What am I seeing the denominator? Well, the denominator, it's cotangent square x. Now, this is the part where you will see, you can either look at it as, well, I mean, it will become a complex fraction, or I'm going to show you all the ways that I can think of. So one way that you can do is that you can say, well, I know 1 over cotangent x, 1 over cotangent square x is simply, tangent square x in the numerator. You can do that. And if you can see it, well, then what's left? Just sine square x. You can think it this way. You're more than welcome to think it this way. If you know that 1 over cotangent square x is simply tangent square x, you can do that. And by the way, look at your notes. For those who don't get 100, there is usually a problem. And I'm going to say this, and I hope that I don't have to say it too many times in the future. Open your eyes and look at the equal sign. How can you allow yourself writing something down that are not equal on the two sides of on different lines of the equation? How can you allow yourself to write something that, well, it is equal to this, but then the next line is totally something else? You cannot, I know that you want to try something just to get extra credit, maybe some partial credit, but still, that's not a good thing. You may do this, set it up as a complex fraction. Well, cosine square x divided by this fraction, meaning that you have cosine square x multiplied by the reciprocal of that fraction. I told you, right? Elementary school math can get you out of this difficult situation of a complex fraction. Nothing fancy here. So still get to sine square x at the end. Make sure you learn how to do complex fraction. It sounds more complex than the name it is. The name is. Complex fraction is not that complex. All right. Tangent x plus cotangent x, not multiply. They're just adding. They're just adding together. So it took me a little while. I was like, do I just change this to tangent, 1 over tangent? Well, you can contemplate that. That will work, but it may take you a longer step. What I realized would be better is to think about this. And then you've got to answer this question. What's the benefit of thinking it this way? What's the immediate benefit of thinking it this way? Well, common denominator, yeah, that could be one, but there's something even more obvious, that this is the way to go. After you have the common denominator, after you have the common denominator, you have something in the numerator, which is equal to 1. Okay. And that's why I kept saying, gotta think of 2 steps ahead. If you don't think 2 steps ahead, you don't know what to do. You need your second step to justify your first step. And that's how you get secant x cosecant x. Okay. For number 5, if I were you, I'm thinking about sine square x over cosine square x, and then 1 over cosine square x. So if I think about this as a complex fraction, and that's how you know you do not change the tangent square x to secant square x minus 1. Yes. Okay. I don't recall seeing anything like this on a test, but you should still know this. Cosine of pi over 2 minus x is the same as sine x. So sine x times secant x, that means it is just tangent x. Number 7, everyone should be an expert for number 7 by now. I mean, I do mean like you can get the answer without actually writing it, the product of the FOIL process. Okay, for number 8, you can do 4 cosecant square x minus 4. What do we do next? All right, I think that's one like this tomorrow. Well, or Monday. Well, if there's no school tomorrow, then we do it Monday. So so this is what? This is just 4 cotangent square x. Okay. Tangent is it an even function or odd function? Tangent, odd function. Therefore, you have negative tangent of x. Number 10 should take you less than 2 seconds to do it. Okay, you just have to see it like, wow, really, really, really. Let's see, for number 11. So if you see your math, you can see this. I mean, if you distribute it, you should see this, and therefore it becomes cosine square x. All right, so this one, 9 minus 9 sine square x, that gives you 9 cosine square x. Now, I would say this is a really good exercise to push your limit, to push your speed limit. All right, this is cosine x times secant square x, which is just secant x. For the next one, this one I would do. This one I would say. Yeah, I'm just going to go ahead and change this for the moment. All right, Don't think there's any other way to go, so I'm going with this. And then I have 1 over cosine x times 1 over cosine x. No, sorry, no. That's actually cosine x. So that's equal to 1. Okay. And then for number 5, it's simply cosine x plus sine x. Okay, if you change the cotangent and change the tangent, it's a very easy way to solve it, to simplify it. And then for number 16, if you change the secant x and cosecant x, then you would also see that it's just cosine x plus sine x. Cotangent pi over 2 minus x is tangent x cosine x. So if you change the tangent x, you get sine x. And last but not the least, this it's 1 over secant square of x. What's 1 over secant square of x? Cosine square of x. Okay, so at the bottom you will see a happy Thanksgiving in reverse. I don't know. I didn't make this. I don't. Yeah. At first, I thought I saw something, but then I was like, I don't know. Now, take out your review. Okay. I do want to go over a couple of things, especially on the graphing part. Now, for the graphing part, I want you to do something for me and for yourself. Now, I would say most of you were able to write out all the shifts, periods, and stuff. Okay. Like for example, what's the period for this? The period for this would be pi. All right. And vertical shift is up 1. Phase shift would be right pi over 2. Now, I don't see a lot of people doing this, but maybe just a few students. Now, you do not multiply the b value back into the parentheses because that's really no point. The whole point of getting the b by itself outside parentheses is to help us see the shifts, especially the phase shifts. Now, what about the vertical asymptotes? Please write the vertical asymptotes based on your graph. That's number 1. Number 2, please draw a graph that matches your information up there. When I was grading the last test, I was like, it's kind of strange how you might be writing a period of pi, but then the graph is totally something else. Okay, that's number 1. Number 2, a few students only, not many, but a few students, you know what kind of graph they gave me for secant? Something like this. And I'm like, really? Like, that's not even a function. Can you see how it's not a function? It would totally fail the vertical line test. And I also want to tell you guys that if you want to do well, you have to know the reasons, such as when do we have the asymptotes, for example. And now, this is a secant function. What did I say about graphing secant function? You think about this as a cosine function, right? You think about this as a cosine function. So the whole midline got shifted up 1 unit. So you plot the points of the cosine function. So cosine starts at the very top. So the amplitude is 1/2. So it should be right here. But then it's being shifted to the right for pi over 2. So that means our first point will be here. And where do we plot the second point? The second point would be plotted here, because that is exactly 1 period away. Like, you cannot be wrong. You just cannot be wrong if you know the period. If you wrote down the period, use it. And these are the highest points. So therefore, in between these two highest points, you must have the lowest points. And in between the lowest points and the highest point, you have the midpoint. So at least you get one pattern down. And where do we have the asymptotes? When the sine graph or cosine graph or the tangent graph, it's hitting on the midline. So you can now start to replicate the graph. Now, I'm not going to spend time drawing all these graphs, completing all the patterns. Now, I want to talk about how to write the asymptotes, because some of you still are having this problem. Now, the way we do the asymptote usually is this. Go ahead and name the first asymptote, which is, where's the first asymptote? Say a pi over 4. We usually use the positive side. It's just more friendlier. And then how often it repeats itself? Every pi over 2, right? So we say k pi over 2. And you want to make sure that you know how to interpret this. K pi over 2 means every pi over 2. Now, some of you would also put this. Okay, or just say k is an integer. That's fine. If you don't write it, I'm cool too, because I know what you mean. But I need you to know that k pi over 2 means every pi over 2. That's what the k it's here for, every single integer. And then just go ahead and finish the parabola-like structures. But the graph has to agree with your information right there. If they do not agree with each other, then what's the point? And for the inverse sine and inverse cosine, now there will be a graph with 2 transformations. 2 transformations. And what do you do first? You always sketch the parent of the inverse sine and inverse cosine function. Okay, you always start with the parent, and then you move on to the transformations.